So we're on the Kinematics number 4 is the new stuff. We're also going to go back to number 3. So water wheels and riding machines, just simple utilities. All these some of the basic principles. Maybe they saw gears, maybe they saw cams, maybe they saw belts. But for whatever reason, with agrarian culture, there's a little bit of idle time. So some of their mechanisms started to turn into trinkets and curios, and I like to call them philosophers' machines. But some of them are just for leisure. Like this is a cam train for the feet of a walking tea servant. A walking tea servant. So it's just like a R2D2 kind of thing. And there'd be, just for show, there'd be like 2 legs that would do an oscillation or a full circle. And they'd have like maybe 3 wheels underneath. Maybe their hands would have a simple mechanism so that when it got somewhere, bumped against something, it would let its hands down. Oftentimes they have to employ a puppeteer or a sculptor just to make kind of like a face, put some clothing on it. So automata are they're oftentimes an attempt to imitate other machines, the given machines like grasshoppers and crickets. This drivetrain right here is one of the first examples of a differential, the kind of thing where if you're going around a curve and your inner wheel is going slower than your outer wheel, then a lot of cars, early Chevys, probably skid. I think it's a little bit more complicated than what's here, but you can see that this side is affecting the lower one, but this is topless, and then this one's connected to this one, so it affects the upper one, so that the left wheel and the right wheel both control the center spoke. Hopefully, I don't know. Oliver, you've understood the drive differential very well. But there seems to be something missing from it, like there has to be like flywheel stuff where it's like one smooth in one direction but picks up in the other. But this particular one is for this guy, which is a always pointing south chariot. So the dynasty's commissions would take one of these with them, and as long as they didn't hit some bumpy, craggy rocks, stay on the flatlands, then it would always point to their return. And you can see how simple it is. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, maybe like 12 different teeth gears. They're really a fun early way to do the gears where they just bore holes and then insert pegs. So you really don't need anything other than just the ability to drill and the ability to peg. But if someone wanted to, you just need the right piece set, and you can make this. This is a Geneva gear. It's kind of an intermittent system. Geneva is just a place where clocks was made, and they started using these kind of strange gears, and so it's just called Geneva gear because it's got an intermittent function to it. So whenever you see kind of like these red bearing crosses, it's another Geneva gear. I'll show you a video of what they're like in action. Ambitious and improbable gears. You might have seen square gears and circle gears. Here's some kind of cam gears. But here's a Geneva gear where it's half in weight and half in go. Here's like 5 of them all together. Here's the first one again. So that fish is like half using. And then he made a train so that 5 are controlled by a shark gear. Just some fun other curios back here. Well, I'm surprised this one works. a pretty cool sine wave. Sometimes say a six-sided object will have like an extra big tooth on the intersection so that it can handle. But I hate to do these by hand. But you can see when he did this one, he showed you a picture, and that you can see it's 3D modeled, so this guy might not be as much of a woodworker as it seems. Here's planetary gears. They're pretty interstellar. Yeah.
Do you think like that has to be made on a computer?
These days, but if it wasn't made on a computer, the tools they use these days to make them. You can always make them out of pine. There's this artist named Bernie Lavelle, and he always hand makes all this gear. Yeah, that was probably prefabricated. You can find the files for these.
So if you want to make something with gears on it, does it have to be gears that you can?
Check out these ones. These are just I don't know, they're the saddest gears. You pick one up and you wouldn't think it was a gear. What kind of program is this? Could you think of that here? I think at this point it kind of proves that anything could be a gear as long as the two are intercom with memory. I get my gears out of Inkscape originally because they just have a gear function renderer. But they don't have a Geneva gear renderer. But once you build your own gear renderer, then it's just a matter of mathematically computing these Geneva kind of concepts instead of the normal tooth. But you can see that these double systems are pretty special. Something like this might be used to kind of like put something in place and then give it some time and then move it on. So a lot of stuff that this book in particular from the source book is interested in is processes for conveyor belts. None of these need a happy face on them. I like this early piston. The worker just kind of lets it ride until it's past the halfway point and then pushes it back and then it'll get a full motion out of it. Probably really heavy stuff, just a little bit of momentum keeps it going. But these pictures right here are just like the primary possibilities. You can remake any of these in GoDo in about five key clicks. To set up sliders, you really got to set up just 3 squares. And you fixate these ones. And then you axle this one to a rod. And then you just have to watch this little corner here. You might even want to shave it off because this stick is only going to get as much play as it gets out. You know, if it's still in expanded walls. Sometimes you have to set up little stops, almost like erasers to erase movement as possibility. Here's like a Geneva kind of systems, but you got access to this on Kinematics 3. The motion renders could be very useful because some of the cooler things in GoDo just emancipate like this exact geometry, but deal with motors on off-ended axles. I'll show you some examples of that in a bit. They couldn't get the wild species to do perfect side profile runs. It's kind of funny. They couldn't go to a tiger or the lion to do the perfect trot. These are all from Moy Ridge, his original work that was commissioned by Stanford. So as you recall, just a triangle with a couple different dots can get you all of these different coupler curves. At the bottom of this page is kind of like a comprehensive example of every single coupler curve you can get from like a class 1 or 2 4-bar. We need not limit ourselves to these, but just straight up, this is what you can get almost computationally by rendering these different lengths. It's kind of neat. But once you have these, then in theory you can kind of like surmount them together, like add these to each other. If we added a warble like this, and then a warble like this. You get kind of like almost like a 3D function. Here's that drive differential again. And this time it seems to have a coupler onto the car's center axle. But just from looking at this picture, it confuses me because if this is moving, say this is clockwise, then that means that this is going to move counterclockwise. Right? But if it was moving this way, that's the opposite of this. Because both of these want to move that way. So if it was spindled accordingly, I don't know how they do it, but if there's like some hidden axle that goes back to the center one, and then this center, or this back one, interact with the right, and this front one interact with the left, then it makes sense. But I'm not sure if there's any ratcheting. I've heard gears grind underneath cars, but I think that has to do with the transmission.
Maybe there's one more in there.
So that's Kinematics 3. Today we're going to Kinematics 4, which is a history of automata. I gave you a slight wink at what automata was, showing you some examples of the T-servant and the south facer, and even this early chariot. So on the automata, you can click on this to odd link. It'll give you a pretty cool PDF. I think it was made about 100 years ago, this particular book. Dear Reader. Reissued. I don't know how old it is. I think it's like 100 years old. I already took some excerpts of it that you'll see interspersed in this presentation. But that particular book is written by like a 1920s maybe historian that sort of knew or knows about automata. Because it turns out that around the Industrial Revolution, maybe like the steampunk people, kind of like the magicians were some of the people that invented these strange machines. Like clockmakers would moonlight as magicians, and then they just start coming up with these curios, and then half of their show would be kind of like showing the Ripley's Believe It or Not stuff off, and then the other half would be doing like levitation. So oftentimes these clockmakers would show up. But that was more in the industrial era. Going back to the beginning, I mean, as far as we can go back is we go to Hero and Vitruvius. Vitruvius was a Roman lexicographer, perhaps. He was doing mechanical engineering. He was an artilleryman. There's a chapter in one of these books that's called like Vitruvius's like the aftermath of his involvement with mechanical engineering. He was the first person to like hypothesize the possibility of steam power, and then it took Huron another 100 years perhaps to come up with an actual model. And you'll see that it's kind of like an aeropile, and the Russians refer to it as the first turbine, but everyone else just calls it the first steam engine, and it's kind of both. Hey, Zoom. So Hero's a pretty cool dude. He's on par with Pythagoras. He didn't have a cult around him at the time, but for what he's offered to kind of like mechanical, Pythagoras offered to mathematical. He invented a vending machine where he could trade a coin for holy water. He really spent a lot of time doing wind-powered music organs and force pumps. He would be commissioned to do public fountains all the time. He invented the syringe. I didn't look up what hydrostatic is, but supposedly it's almost like a perpetual motion machine where the fountain's kind of self-contained. Maybe it just has one pump returner. But it's different than having like a river kind of, a Sturbridge kind of thing where you're not controlling your own water. The water is just given. I've gone around the internet a couple times to find Huron's works, and I just stumbled upon them yesterday, and they are only in Greek, Arabic, and German, and French, which doesn't really help us at all. But this is the website for it. And all these volumes are pretty cool. You don't even need for the mathematical ones, you really need to read them, but for the mechanical ones, and especially the one about pump systems, I just extracted all the pictures so you could see what he was up to. So this is 2,000 years ago. Here's an example of kind of like a water or steam-powered organ. This is the aeropile. Basically, you just have a cauldron of fire, and then you have like a steel brass sphere with these two pipes coming out at kind of opposite parallels. And then heat it up enough, and if things are balanced, it might be on a little bit of gyro so it can spin. If you do it right, then it just starts spinning out of control. I don't think they harnessed it at all in this first principle. It was just kind of like an oddity, just how electronics was kind of like a parlor trick 150 years ago before it turned into something functional. But here it looks like he's got an aeropile or something inside of the basin. This reminds me a little bit of the ducking water bird. There's this chemistry experiment that turned into a pop culture toy where a bird just using some thermodynamic laws of evaporation and weight displacement can just duck infinitely, kind of, as long as it has water and evaporation. And you'll see that later, but look at all these pictures. These are all the things verging from founts and pulley systems that Huron was coming up with 2,000 years ago. Interestingly, it's really integrated with Greek pottery. These are called crators, and it's just funny that his engineering drawings were done with water carrying vessels. Here's a door opening system. Hard to believe that they would employ phonemics to do that. But you click on the right volume over at Namaste over here, and you can get the original documents. A lot of the systems had to do with this is like what automata might have been at first. It's the ability to imitate drinking or biological functions. Maybe the first septic systems. Certainly, Vitruvius did a lot of stuff with the hidden within the walls of what was then like modern housing. Like, what if you excavated? And in the basement, you had all the mechanics that would do central heating. So you'd have like an insulative middle wall area where hot air could be flown through. And I've experienced that in German bathrooms where you walk in and like the floor is hot because there's like some kind of undercurrent of hot air in the house underneath the tile. And here's an early automata. I think this little trigger to represent a hand is going to accomplish like a human feat, maybe like this eternal dialogue between the serpent and the fighter. So it's early home automation. He was the first one to lift large loads with corkscrews. He'd invented pulley systems that would just fractionize the load so that the human input would just have to be within our reach, and we could do kind of colossal industrial activities. He might have invented, or at least refined the press. You can just think of all the economy of olive oil, how it would just change as soon as they refined a new version of the plant press. This gear train box looks a lot like the one I was building for school. You can see my laser print is right here. All these holes are for the axles for these gears, and then each gear has a mini gear on top of it to step it down. Four-sided box with an open edge. See, this piece right here is got an open bevel so that the front of the box can have a linear actuator. You notice an arm. You can see 4 of these boxes underneath this table. This is a little installation art piece I was attempting to make these waves move up and down, and then these might be covered up in spandex or something with powerful enough motors and sturdy enough balance. As you can see, it's the same problem with trying to make a slider. Each one of these is trying to be a slider against the wall. And then there's like a guide. Each one of these is kind of like a closed eye that they can roll up in. But it would teeter-totter. It's really hard to get stable sides. But he would use very similar possibilities. So this would be a hand crank on a universal screw, and then the load is lifted quite well on the opposite side. There's tons of variations on that that would go up to the size of cranes, so that two people would practically be like horses on a high corkscrew, and then up on the top of the corkscrew there would be a sliding bolt that would sustain all the weight of what they're lifting. But from these pictures that are 2,000 years old, you can think of like they must have known how to do glass work to make vials, they must have known how to do metal work to make steel components. But I kind of left the Renaissance for another day. I wanted to go straight into kind of like 16th century when automata started to really take off. I don't think in the Renaissance they had enough time to just hang out and make automata. They were so hard pressed to make realism and to fight some wars for democracy, say in like Florence, you know, where Enlightenment was kind of happening in the Renaissance period. So these monks, 16th century, this is the monk bot. I'd like to introduce you to the monk bot. It's like 4 feet tall, maybe. I want to hear like Gregorian chant while this guy's walking around. Spain, 1560. He beats his chest, he raises the crucifix. Here's him cast down. Maybe he's like bronze plated. He's got a wind-up crank on his side. I think this would be really, really effective if you had like say a cathedral out in the middle of nowhere, and you just always wanted a monk that was votive. Sumerians would make votive figures that would just hang out outside of their churches and cathedrals, and these like large-eyed totems would just be praising or just they're like advertisements for what you're supposed to do. They role model these automations. So from a distance, if you're eyeing this place, there would always be this character that would walking to and fro around your cathedral, almost like an eternal worshiper. You're pretty scared right there, huh? But all it takes is rotate the neck, rotate the mouth, rotate the neck on two. It's kind of like got a bearing. Inner workings, it's got a kind of like a ratchet on the bottom. Chains pulling up and down on the arm levers. I'll show you an example of those in a bit. But you can see this is some technical genius 400, 500 years ago. Metal smithing. And all it does is pivot around on a couple geared wheels on the floor, and then the feet are superficial. Same as the T-Monk. Superficial feet. We didn't quite master that. Even the new kind of like Suzuki and Yamaha robots, they walk really slow. I hear Japan is sending a robot into space as an astronaut on a mission. There's 2 or 3 humans, and then there's the robot that is an automaton, can kind of walk around by itself, think for itself supposedly, whatever that means. So it's a tank-like tripod roller, patch chest, foot oscillation, mouth oscillation, indeterminate trajectory. The other one I got some info about that was in the 100-year-old book. It was about the Turk. The coolest anecdote I found in the book the first link on this page is about how Napoleon Bonaparte played the Turk, and there's a small child. It's just like a chess master inside of this box that turns gears to make the automaton play chess above. Maybe there's like a mirror so that the person can see what the board is. Perhaps they're just looking at the grating underneath the board. I don't know how they stop themselves from breathing or sneezing. But supposedly this ruse went on for a couple generations. The first magician showman that invented it, he tried to sell it for 20,000 francs to the guy that invented the metronome. And then it ended up that like after he kind of retired, his son had to sell it for just 10,000 francs. And then the metronome inventor had to fix it up for its next round as a public curio, like a traveling caravan. But the Turk would roll through town, and when it played in Russia, the queen said like, "Wow, that's great. I want to buy it." And when like the queen of Russia says she wants to buy it, it's really hard to get out of that kind of agreement. But the Kempler guy that invented it, he said, "It can't work unless I'm here." So, and he didn't want to disclose that there's a kid inside, because then you probably get killed. But when Napoleon played him, supposedly, just regularly, like the Turk always went first. It was just customary. I don't know why. And Napoleon decided to go first. And then everyone was like, what's that going to do? Like, if this is an algorithm, what's it going to do if it has to respond to the first move? And then Napoleon kept making erroneous moves. And like the first time he did, the Turk was known whenever a erroneous move happens, he goes over and knocks it over. But Napoleon was just testing, he's all gall and spite for being such a tyrant. And he just kept doing an erroneous move just to see what would happen. And then after like the third erroneous move, the Turk just swiped everything off the board as if he'd had enough. So it's an interesting idea that the machine had had enough, despite not even being a machine. But back in history, the Greek culture, the book references, it just gives you this picture, and then it says that they would make kind of like sex automatons for like public Baccha festivals. And it says that they're lewd to the point where there's not even going to talk about them further. But you can just imagine what automatons can do. A lot of this stuff's out of a online resource called Chloe in Germany, who just invents little kits out of wire and circles, and they've accomplished like a lot of broad range of motions. This one is a dual cam, so it rides on this cam when it's the priority, and it rides on this cam when it's priority. So it's like a double jump, 1, 2. So it's almost like composing at this point. And this guy is just on just a standard up and down motion. And then this one's you just think about the axles. This indicates like this is a worm in the ground, and like pulls on it. And if you put some axles on it, then the mechanism or the bird's body will try to recoil instead of just up and down. It has to defer the movement. And this one's pretty cool too, because these two stabilizers keep the wings from changing as much, and then just the soft movement of the body makes it so that the wings always stay here, but relative to a body that's above it, and then in the middle of it, and below it. And of course, when it's in the middle, then it broadens out. So that, and then it tries to squeeze out and goes down like that. So in the web, when they do these examples, they'd have a lady that was showing you like, well, what's the motion we're going for? And she'd just be like this, and then she'd show the automata. And this one's just going for broke, just putting 3 ups and downs on different phases right next to each other. The other side of it just has three gears. This one was pretty cool. This crab, it's got the up and down thing, same as the bird, and then how this one's got its wings that are supposedly set. For this one, it's got 6 crab legs, so it kind of does this really cool kind of like surfing thing where it's just like a little more human than you think. So here's another picture of the drivetrain where they have 2 cams that commingle. Here's what you can do. You can do a caterpillar emulation by just doing rows and rows of cams. and then all those sticks are just the exact same diameter as the drill bit, and then that material there is at least like a 1/2 inch. So ideally, you know, it's exactly flush so that the poles don't even have to be mechanically connected, they just rise and fall. It's the kind of thing where if you took the drivetrain out, then the whole caterpillar would just fall to the bottom. And I really like this one. This is the back side of it. The other side is like a sheep. And then these two guys work together so that as soon as this spiral rotates past the ratchet, it's got a spring to gain tension. And then once the ratchet tooth goes past this point, then instantaneously like the head cranks forward to like bite, and the jaw flaps, and then the a little dog on the other side, you know, flips out, gets out of the way because it's also on a spring. So I took some screenshots of the book on paragraphs that discussed some of the cooler things that were accomplished by these curios, these automata. Supposedly the astronomically impossible one that they mentioned for Louis XIV was that someone made like a ticking time clock like court group. Say you have like 2 cavalrymen and a couple of automatons, one for the princess and one for the waiter guy, and then they have a carousel, and then they have 2 horses. Now imagine like all the machinery that would go into making all those characters. Supposedly it was small and had the ability to like go to the end of the table and then do edge detection to find out if that was the end of the table, which you can imagine you could supposedly accomplish just by doing like a tension indicator. Like if you have tension on the ground, then you're safe, but as soon as you go over an edge, then say, okay, go to mode 2 or whatever. But supposedly then it lands in front of the king, and then like the characters get out, and then, you know, it's impossible, like hard to believe. There's lots of other superstitious illusions of grandeur. But like edge detection, like what was the first automaton that could accomplish that? That's something that's doable. These creators would create talking machines where you can imagine different bellows that had reeds on them, and if they're finely tuned enough, you can make a voice out of just a couple oscillators. So this one says 3 different wind chests, one loaded with a weight of 4 pounds, 2 at 2 pounds. The wind chest communicated with 3 little chambers in the body of the figure, and these chambers were all connected. The barrel worked upon a screw bearing similar to the cylinder of a phonograph, so that the revolution of all its levers described a spiral 64 inches long, and as the barrel rotated during performance, made 12 revolutions, the lever passed over a distance no less than 768 inches. So some of these machines, the coolest ones, were drawing machines, were writing machines. And the most famous one is like a dummy of a character with one arm that has a pen, and then underneath it is this slew of gears, all this brass memory, they call it. The most famous one that was for Louis XIV was the duck. Here's all the stuff it could do. And the same thing, it's just a little automaton that has like sticks connected to it, and all those sticks and gears are underneath like a giant computer-sized box. Having been wound up, the duck ate, drank, played water with its bill, made a gurgling sound, rose up on its legs, sat down, flapped its wings, dressed its feathers with its bills, performed all these operations without requiring being touched again. The duck, they spent some time talking about digestion, because if you're going to emulate a bird, then you're like, well, what is it going to do to eat? And on the end it says, I don't pretend that this is perfect digestion, but he did have enough so that the machine could like receive a piece of corn, snap at it, and then somehow tip back so that it fell into it, and then there'd be like some churning tubes inside of it. So all he was after for emulation of eating was just reception and crunching and then evacuation. But they went through great lengths. And you wonder how much closer we could get to it now. This other guy, Balkanson, was another kind of big figure. Ledroys was another one. They all of them were kind of like, they'd have a drawing machine. They would have curios. Kind of like a menagerie of automatons. sometimes they would develop out of cuckoo clock making. On the hour, you'd want a montage of activities to happen. And back in 2000 or in 0 BCAC, when Heron was doing his thing, one of his best works was he worked in theater, and he just created an entirely automated performance that lasted maybe 20 minutes or so. And it might have just been figures that, you know, moved their hands up and down, walked around. And one particular event that he added to it was sound control, where he would have a bunch of steel balls that would drop on like a steel plate at a specific time to represent thunder. So if you just set up enough of these kind of mousetrap Rube Goldberg automations, then it's just almost like a modern day Disneyland ride. Here's one that impressed the author of the Curios book. Different diagrams for a automata that can go downstairs backwards, do somersaults. With the right springs, it can do it all by itself. But it's all about making the machine interact with the world in a way that parallels how we react to the world, and just as technology was developing, like how good is our technology? Often the same question is how well can we recreate ourselves in the world? So this guy Kempelen made his fortune just by traveling around with this machine, deluding people in the first artificial intelligence program. But it really has to go back to these drums, data drums, this cylinder of timing. The programming language I use is called MaxMSP, and before I got into it, it was a musician's tool for programming music, and the primary method of using it was to use a scheduler or just use a timeline, which looked exactly like this. It's just a spreadsheet, and then all of the ons would be black, would be notes, would be like triggers. All the whites would be offs, just sustains. So this was just how people thought for the longest time. It was just in a spreadsheet, in a grid. Control systems. And then each line just represents one increment of time. I don't know if these are gremlins or demons, but in these very early drawings of machines, which you could certainly Google date if you just dragged and dropped it into Google again. But you can see that it's just monumental. But how far does this go back? What does it predate? Think about linkages in shadow puppet design. I think it's in Indonesia they have a popular theater form where it's they might doll these up with articulate designs, but really all you're going to see for the show is the shadow. And these characters are just held up by linkages, and they just be paper stencils. A lot of early, in the Hugo movie, you're also going to see kind of like giant scaffoldy kind of dragons where a person's inside of it and they have like clenching teeth, and then there's arms and legs on sticks. And those are theater productions like dragons and monsters, and even like the Chinese New Year dragons. Like all of those are just other examples of automata, or just animating the world or any kind of. This is a patent for the. Maybe it's an improved version of the fist punch mechanism. You have to really look deep into it to see how in this patent form there's a dotted line that represents specific components. And now you see how this one's curved and how it's hollow. So this is a hollow arm with like a curved piece. So you can imagine once this extends to its entirety, then this bicep curve might be in the exact same place as this bicep curve, the one inside and one outside. So it might take a little bit of understanding to realize what these dotted lines are doing. But basically, you pull back, and then the arm rotates, and then the rotation of this fulcrum extends to the next one. Here's another side view of it. I think that one's patented for whatever reason. It's a little bit more complicated than the straight-up punch doll. This is the best one I found on the net. And luckily, they gave you this picture, which shows you what you got to do. between these two pictures, I was able to reconstruct it in GoDo. Here's an example of what someone thinks is going to be the gear train to make a horse move. Here is that triangular coupler curve in GoDo I did an example of. You can even click on this and download it. There's 2 GoDo files for you to download. There's that one, and then this is an escapement that I found online that someone did in GoDo. The pendulum just goes back and forth, and the trick is this little caliper thing. So it's like a four little lines that make this kind of tooth that goes clench, 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 and it slowly just rocks down to let one through at a time. But you got to click on this one. This is the one that I'm proud of. You know, might load now. GoDo. And it's an example of the punch mechanism, but it's you know, the proof's in the pudding. If it's in GoDo, you can just see where the linkages are. So just so you know the basics, we got an axle, an axle, an axle, an axle, an axle, 2 fixates, a spring, and then this is a 4-bar linkage. But strangely enough, like one of the bars is 2 points on this circle. The motor's on the big axle. And the only difference between these two, I made the one on the right first, put a spring on it. The only difference is that I had to tweak the principles of this guy. Oops. If you want to put your edit window in a fixed position, then you can press that. It's what I like to do if like the right click's not working. But if you ever want to go to properties, you just go in here. Every object will just replace itself on the 3rd below the line. And so the spring constant's at 60. Dampings, I don't think I changed. Target length is 2.4. So target length means how long it wants to be. And then maybe spring constant is how much pressure it has. So you can see that 60 and 2.4. And then over here on the other one, it's 180 and 1.6. So in play mode, you can see that one-way recoils, and then you let go. The one on the left wants to tense, and the one on the right wants to extend. So you can choose which spring you want, and then if you press right, then you extend. If you let go, then you release. So the one on the left seems to be the one that you'd want in a punch glove, but if you had a blocking arm, you'd want the one that was out to sneak back in to protect your face. And their mechanism might be a little bit more complicated, but if you just check out the net, you can see that they have a Rackham, Sock'em. I think there's better ones than that. Let's just put it in the box. Or yeah, there is a demo for the Rackham Sock'em robots that look pretty professionally done. Here it is. It's nothing to write home about. Sometimes they over-design these to the point where you can't really get into them and feel like you can understand them. So like I'm pulling the character apart, you can see he's got a lot of tension on a couple of his parts, and now he's broken practically. But the principle for this guy, you know, just like I was showing you, is you got a block move, you got a punch move. So, yep, they keep playing. Supposedly you hit the head out. If you looked at the mechanism in the head, you see it's got like a tooth thing. So maybe if enough teeth fall out, if the head gets lodged too high up on the slide, then you win. It might have a reset function in it. Not too good at this game. But zoom in and see that it's all just components. But look at all those fixates. When you click on something in GoDo, it'll click on like all that's part of one unit. some of the stuff I wanted to mix in GoDo is create kind of like really big objects. And I'm wondering if you're allowed to make two objects that aren't touching still fixated together. Because the limitation with GoDo is it's as dimensional as I try to get you with layers, is you're still just one layer at a time. And you know, in theory, two things that aren't touching. You know, that they wouldn't be able to fixate together. Maybe if there's a plane on another dimension and then you fixated those to that, then you'd be safe. A lot of the early stuff that, like the air pile that Heron did, some of the early phonemic stuff you could redo in GoDo, because they do have the water function. But jumping into contemporaries, Doug North is the artist that I think that they commissioned to do the stuff for the Hugo movie.
When I discovered contemporary automata, that it all sort of clicked for me. I'm like, oh, I can put them all together and give them motion and learn a little bit about mechanics. Automata, you know, it basically means self-moving. And so it's typically associated with a clockwork mechanism. My work is more of a contemporary form of automata. There is a hand crank in which you actually turn the mechanism and bring the thing to life that way. You can hear the mechanism working. In this case, it sort of worked out to my advantage. The mechanism that I've incorporated to make the dog bark in a sort of sharp and snapping way also works out to coincide with when his mouth opens, so it creates something of a barking effect. You run this cable down your back and then down your sleeve, so it's pretty much completely hidden. And whenever you feel like it, you can squeeze the handle, and out pops the monster. And hopefully he looks relatively angry. This is a prototype that I'm working on, a rather advanced mechanical prototype that represents a carnival sideshow scene. When it's finished, I'll have these, painted in full color, but I'll give it a crank so you can get a feel for it. There's a whole second scene going on. So this is the Air Lofts building, which was created as a work-live space in Lowell, one of the very first. And so I was very attracted in the building as a whole, and then I had the opportunity to come and view this unit, and I saw this, which is the original walk-in vault from when this was a patent medicine company. This is the original door, probably weighs 500 or 600 pounds. If we open up the second inner door,